Number 1, explain why a sample of pure water at 40 degrees Celsius is neutral even though the concentration of the hydronium ion is 1.7 times 10 to the negative 7. You're given the Kw. Remember that Kw is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. Neutrality is when the hydronium ion concentration is equal to the hydroxide ion concentration. So since we're given our Kw and our hydronium ion concentration, let's calculate our hydroxide ion concentration, see if they're equal. When I put that into the calculator, I get a hydroxide ion concentration of 1.7, and in my calculator it's actually 0.588, etc. But 1.7 times 10 to the negative 7. That meets our neutrality definition. Number 2, the ionization constant of water, 2.9 times 10 to the negative 14 at 40 degrees. That was given to us in number 1 as well. They're asking us to calculate the concentration of the hydronium ion and the hydroxide ion, the pH and the pOH for pure water. Well, we've already calculated the concentrations of our hydronium and our hydroxide. But if we didn't have that already, if we didn't have 1.7 times 10 to the negative 7 to start with, then what I would do is I would assign each of these an X. Remember, the autoionization of water looks something like this, where we form the hydronium ion the hydronium ion and the hydroxide ion. Now, if I let X represent the amount of substance we have in equilibrium, then my Kw is then equal to X squared, because X times X is X squared, and that equals a value. That value is 2.9 times 10 to the negative 14th. So when I take the square root of that value, I get 1.7 times 10 to the negative 7. Now, because the concentrations are equivalent, we can say that the pH is going to be equal to the pOH here. And in this case, it's going to be 6.77. For number 3, we're asked to basically do the same calculation at a different temperature. So here the Kw is equal to 9.614 times 10 to the negative 14. Now, we've already shown that that should be equal to X squared. So if I take the square root of these values, then X, which is the concentration of my hydronium and my hydroxide, should be equal to 3.100 or 01 times 10 to the negative 7. Now, that is the concentration of both hydroxide and hydronium. So when I take the pH, and I need the negative log of that value, I get a pH, which is the same as pOH because I'm working with the same concentration here. That is 6.508. Number 4, we're going to be using the equation pH equals the negative log of the concentration of the hydronium ion. Now, if you've been through other chemistry courses, you're going to be moving on to other chemistry courses. Please note that this is equivalent to saying that the pH is equal to the negative log of the hydrogen ion, the concentration of the protons. It's saying the same thing. So what we have here is HCl, and we are told that everything is going to ionize completely. So here we have HCl, and that's going to dissociate into hydrogen ions and chlorine anions. This is a 1-to-1 relationship. So our concentration of HCl is the same as our concentration of our hydrogen ions. So I'm going to plug this value, 0.2, into this equation. And then I get the log value. So the pH is going to be equal to 0.699. That makes the pOH 14 minus that 13. Now for B, we have a sodium hydroxide solution. So sodium hydroxide is going to be splitting into sodium and hydroxide ions. So this time, if we take the log of this value, what we're finding is the POH. So the POH, which is analogous to pH, we're going to take our 0.0143 and plug it in for this value. And when I put that in the calculator, I get my POH of 1.845 is what I'm going to call that. And then my pH would then be 14 minus that value. I get 12.155. For C, I have an acid. So here I have nitric acid. That's going to dissociate, so I have my hydrogen ions and my nitrate anions. So when I take and put 3.0 into this equation, I get a pH value, and that pH value is actually a negative 0.48. That means my POH is then going to be equal to 14.4, I get 14.48. Now for D, I have calcium hydroxide. Now the calcium hydroxide, you need to be careful with this one because that will dissociate into calcium and 2 hydroxides. So because we have a 2 for our stoichiometric ratio here, you can use a little bit of dimensional analysis. So if I have 0.0031 moles per liter, and in 1 mole of calcium hydroxide, I have 2 moles of hydroxide ions. So that makes the effective concentration that I'm working with 0.0062 capital M molarity of hydroxide ions, and that's the value I'm going to put into my POH equation. So that gives me a POH value of 2.21, and that means my pH value is then 11.79. Number 5, calculate the pH, POH of each of the following substances. Substances ionized completely. Here we have a monoprotic acid. That's an acid that has 1 proton to give, so 1 hydrogen. It's going to ionize completely. That means in order to find the pH, I'm going to use the standard pH equation and insert this value, 0.00259, into the calculator. And when I do that, I find that the pH is 3.587. That means the POH is 14 minus that value, or 10.4133. Here for sodium hydroxide, that's going to break into sodium and hydroxide ions. So when I put this value into the P equation, I get a POH this time, and my POH is then going to be 0.678. That makes my pH 14 minus this value, which is going to be 13.322. Now for C, the barium hydroxide, like I showed up here with the calcium hydroxide, has 2 moles ions for each mole of barium hydroxide. So that means I need to use twice this molarity. So when I put this into the P equation, I'm finding the POH because I'm using the concentration of the hydroxide ion. And I'm finding a POH of 3.85. That makes my pH 14 minus this, so that should be 10.15. For D, my KOH concentration at 2.5, it ionizes completely. It's a 1-to-1 relationship, so that means the concentration of my hydroxide ions is also 2.5. Put that into the P equation, and I get a POH value of negative 0.400. So my pH is then 14 minus this, which would be 14.400. And I may have rounded this one incorrectly on retrospect. It looks like the pOH should be a negative 0.398, which would make the pH 14.398. Number 6, what are the pH and pOH of a solution that's 2.0 molar HCl, which ionizes completely? Well, I'm going to take, for my pH, I'm going to take the negative log of the concentration of my hydrogen ion here. And here, since we're told it ionizes completely, this is a 1-to-1 relationship, so I'm taking the pH, I'm taking the negative log, of 2.0. So that means my pH is equal to a negative 0.301. That means my pOH is 14 minus this value, so 14.301. Number 7, what are the hydronium and hydroxide ion concentrations if a pH of 6.52? Well, I need to take the inverse log here, so I need to take 10 to the negative 6.52. And what you should get when you do that is 3.02 times 10 to the negative 7. Now that is the concentration of the hydronium ion. So to find the concentration of the hydroxide ion, you need to remember your Kw expression. Remember, Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. Since Kw at 25 degrees, because we aren't told anything different, so we can assume 25 degrees, is 1.0 times 10 to the negative 14, we can then plug in that hydroxide ion concentration and solve, our hydronium ion concentration, and solve for our hydroxide ion concentration. So we divide 1.0 times 10 to the negative 14 by this value here that I had just left in my calculator in order to avoid rounding error. And I get 3.31 times 10 to the negative 8 is equal to my hydroxide ion concentration. Number 8, we're referred to figure 1 in order to find the pH from wine. And in number 9, we're supposed to find the pH of lime juice. So I'm going to find them both over here. So wine is somewhere between 3 and 4. I'm just going to call it 3.5 because I'm not sure. And then lime juice is found up here. Lime juice is pretty close to 2. I'm just going to call it 2. So I'm going to assign this a pH equal to 2, and this I'm going to assign a pH equal to 3.5. So now I can calculate the hydrogen ion concentration as well as the hydroxide ion concentration. And here I just want to point out, it specifically says hydrogen ion, but in 9 it says hydronium ion. I need you to be flexible enough to realize that they mean the same thing. So for number 8, we have a pH equal to 3.5. We need to find the hydrogen ion concentration or the hydronium ion concentration. And so what we need to do is take the inverse log of the negative pH. Remember, pH is equal to negative log of the concentration of the hydrogen ion. So if we have our pH of 3.5, we need to multiply both sides by -1. So now I have a negative 3.5. Now I can take that inverse log in order to get that hydrogen ion by itself. And when I do that in the calculator, I take the inverse log of a negative 3.5. I get a hydrogen ion concentration of 3.16 times 10 to the negative 4. Now that means my hydroxide ion concentration is going to be the Kw divided by this. So 1 times 10 to the negative 14 divided by this hydrogen ion concentration gives me hydronium of 3.16 times 10, this time to the negative 11th. Both of these have units of molarity, capital M molarity. So for number 9, we're going to do something very similar, except my pH, because it looked okay, I'm not sure, but I'm going to call it 2.0. So then I can find my hydrogen ion concentration by taking the inverse log. So on my calculator, again, that was second and then the LOG button. Then I have my change sign button, my negative, and the pH, 2.0. So I get a hydrogen ion concentration equal to 0.01, capital M molar. That gives me a hydroxide ion concentration when I take my Kw, 1 times 10 to the negative 14, divide it by this, I get a hydroxide ion concentration of 1.0 times 10 to the negative 12. Number 10, the hydronium ion concentration of a sample of rainwater is found to be 1.7 times 10 to the negative 6. What's the concentration of hydroxide ions? Again, we're going to be using this water constant expression. So if I have hydronium, I can find hydroxide, and that's by using Kw. So Kw is 1 times 10 to the negative 14. If I divide that by the value that I know, my hydronium, 1.7 times 10 to the negative 6th, I will be left with my concentration of hydroxide ions, which I get to be 5.9 times 10 to the negative 9, capital M molar. Number 11, similar situation. This time I have hydroxide, and I want to find my hydronium. So here I'm going to take my Kw, and I'm going to divide it by what I'm given, my 3.2 times 10 to the negative 3, and I will be left with the concentration of my hydronium ions. So when I put this in the calculator, I get a hydronium ion concentration of 3.1 times 10 to the negative 12, capital M molar.